Hello, everybody. Hi, I'm Duncan Swinson, Chair of the Northwest RINA branch. Welcome to our third lecture on the design of an offshore wind farm, kindly presented by Rupert Berryman. And over to you, Rupert.
Thank you very much. My name is Rupert Berryman. I started working on renewable energy in 1996 when I built an onshore wind farm. And this gave me a great appetite for renewable energy, which I thought was a fairly worthwhile career to follow. I was about 52 at that stage. I was 52 when I built my first wind farm, and I made a career in renewable energy from then until I was nearly 70. And this evening, I'm going to show you, to start with, an early onshore wind farm. Then we'll work our way through early offshore wind farms and their construction until we get to the turbines that we are now installing. And in the last 25 years, wind power has progressed in leaps and bounds, absolute leaps and bounds. I wouldn't have believed it. Anyway, I'll share the screen now and we'll have a look at some of my slides. Okay, so 28th of January 2021, Rupert Berryman. I'm a member of the Royal Institution of Naval Architects. You may remember Trevor Blakely when he was chief executive. Trevor Blakely and myself joined the Navy on the same day, I think on the 19th of September 1963. That wind turbine was erected in 1996. The short video I showed you was taken in 2016. The wind farm was live for 20 years and it's still going strong, and it's going to be allowed to remain where it is until 2025. So it's got a 9-year stay of execution. The availability to start with was about 93%. It's 97%. It's dropped now to about 93%. But all 36 wind turbines are still running. So this is Windy Standard Wind Farm in Dumfries. And 36 machines we put up in 1996. Each of them was 600 kilowatts. 600 kilowatt machine was state of the art at the time. So from the 36 machines, we got 21.6 megawatts, which isn't a great deal. It was the highest wind farm in Europe when it was built, 610 meters elevation. And the foundations were rock anchored. I'll go into those in a minute. The weather conditions up there were fairly hostile. It was in the wilds of Dumfries, and 90% availability was achieved to start with. And it says something for the wind turbines that they were put in 1996, 25 years ago, and they're still going strong and still producing a reasonable amount of electricity. But we'll work through the size of wind turbines as we go on through the talk. And you'll be quite impressed, I think, by the way that wind turbines have advanced. The foundations were made of concrete with an embedded cylinder. And the embedded cylinder is really part of the tower. The tower just bolts onto the top to a bolting ring on the embedded cylinder, and that shows the rebar before it's lowered into a hole. And there we are, ready to pour the concrete into the hole around the rebar and hold the embedded cylinder in place. Now, normally, or quite often, you would use a complete concrete gravity structure for the foundations of wind turbines. And in this case, it would have been about 120 cubic meters of concrete. However, we used rock anchors, which are like long raw plugs, 20 meters below the embedded cylinder, and they are grouted into the ground. We'll go through that in a minute. But there you can see the bolting ring on top, to which the bottom tower section is bolted to, and the rebar and the conduits for the rock anchors ready to be drilled through. And there we have a concreted in embedded cylinder and its rebar, and the conduits are being drilled through to a depth of about 20 meters to insert the rock anchors. I'm not sure how many people are familiar with rock anchors, but it's like a big raw plug that's lowered into the ground. It consists of wires, wire cables, and grouters poured round them, and there's a clamp put on the top with collets, and the foundation is pulled down by using collets, and then they're capped off. But instead of using 120 cubic meters of concrete, all we used was about 55 cubic meters of concrete. Didn't actually make the foundations any cheaper, but it just meant that we had to haul a lot less concrete from quite a long distance away up to the wind farm. And the wind farm was 7 miles along forestry roads off the beaten track. And there you can see the capped off rock anchors and the transformer sitting in the sitting on the concrete base inside the embedded cylinder, ready for the tower to be put on top. One shortcoming of this wind farm was that you couldn't get these transformers out through the door, and if you needed to get them out, you had to take the wind turbine down and remove the tower sections before you could unbolt them and lift them off. And this caused us a lot of trouble, because we got trouble with the tap changes arcing and the oil in the transformer casing gassing and causing the transformer casings to split. And it happened on a number of transformer casings, and we had to lift the turbine towers off again and change the transformers out. They wouldn't go through the door. The tap changer design was not particularly slick, and they improved the tap changer design so that it had less wires in it, going around less angles at the top of the transformer casing. There's a tower lift with 2 cranes, bottom tower being lifted. Quite a simple procedure, upended on the bigger crane, which eventually supported it from the top, tower lowered into position, and the bolts, there's a bolting ring at the bottom, bolted onto the embedded cylinder. Fairly straightforward stuff. And there's a rotor being put up. Now that's quite a small rotor, because all these wind farms, although they were these wind turbines, although they were state of the art at the time, the rotor diameter was only about 47 meters, 45 meters. And there's a view of the spine road and the turbine spurs coming off it. And it's best to make friends with the locals when you're putting an onshore wind farm here then. And we got a very good rapport going with the locals. We took them all up there in a coach and showed them our wind farm. And most of them had never been up to that part of Dumfries in their local area before, and they were delighted to come up just to see the view. I'm not sure that they were too bothered about the wind farm, but they thoroughly enjoyed their half day out, being taken by coach up to see the wind farm, and it made us very acceptable to the locals, who were delighted to see us there and so much activity going on. That's a rather nice shot of a wind turbine. That was the highest wind turbine in Europe at the time, just over 2,000 feet. November 1996. Now, how much power did we get from this state-of-the-art turbine? Each turbine was 600 kilowatts. Capacity factor or load factor was 0.3 or 30%. I'll explain what load factor means. If you have a 600 kilowatt turbine running for a year, it will produce so many kilowatt hours of electricity. Now, the wind doesn't blow all the time at 15 meters a second, which is the requirement to get the full output from the wind turbine. Sometimes it doesn't blow at all, and other times it blows at a lot less. So the percentage of the annual output that you could get from it, if the wind blew at 15 meters a second all the time, is 30%, because the wind doesn't blow at full chat the whole time. I hope that's as clear as mud to everybody. Can you nod if it is? Yeah. Power a year per turbine is what's happened? Oh, okay. So many kilowatt hours. One home uses on approximately 4,000 kilowatt hours a year. So the home supplied by one turbine is 394, and from the 36, it was 14,184 homes in theory. This was a very early wind farm, and things have progressed since it was built. However, it's still operating, well, now 25 years on, so it's doing okay. I'm very proud of it. There we see the inside of a wind turbine, which is really quite simple. We've got obviously a rotor rotating at, say 20 RPM, or for the new big ones, 9 RPM. Something like a propeller shaft from a ship, taking the high torque from the rotor to the gearbox with a triple speed up gearbox, normally two epicyclic stages and a parallel stage, and driving the generator, which is probably rotating at something like 1,000 RPM. The wind turbine always faces into wind, and there are yaw motors and a toothed ring inside the nacelle, and the yaw motors key onto the toothed ring. If I can find the cursor. Oh, there we go. The yaw motors key onto the toothed ring and have the wind turbine always facing into wind. And we have some often electronic wind measuring devices on the back of the wind turbine. There's a weather vane and an anemometer. And the anemometer will start and stop the wind turbine depending on the wind speed. And you normally need a minimum wind speed of 3 to 4 meters a second before the rotor will produce enough torque to produce electricity. The wind turbines, the early wind turbines, do not work unless they're connected to the grid. You have to have power flowing onto the stator of the generator before they will work. It's if you haven't got them connected to the grid, you can hang on to the positive and negative wires, as it were, coming down from the wind turbine, and they won't give you an electric shock. You need to have the wind turbine connected to the grid. They're called asynchronous wind turbines. Now, not all wind turbines are quite like that. Some of them have a large diameter rotor or a large diameter generator without a gearbox. But you may have seen some of those. They've got a more egg-shaped nacelle than that one. But they're a good alternative. Enercon in Germany make gearless wind turbines, and they generated a funny form of AC and go through a rectifier and then have a static inverter. Maybe I've lost some of you, but I hope I haven't. If you understand what a rectifier is and what a static inverter is for converting DC back into AC, slave to an electronic frequency generating device. Now we move on to offshore wind farms. This is Horns Rev offshore wind farm, which completed in 2002, comprising of 80 2-megawatt machines. So we moved on from 600 kilowatts and we're up to 2 megawatts now. 2002, 2 megawatts, 1996, 600 kilowatts. And people, when we had 600 kilowatts and got to 2 megawatts, said, we'll never get wind turbines bigger than 5 megawatts. And next year, someone produced, or Vestas produced, a 3 megawatt wind turbine. You can see the position of Horns Rev on the map with the little red dot. And that picture was taken under very humid atmospheric conditions, and it shows the air being compressed behind the rotor and then decompressing and showing the fog that you can see. And you can see how the wake effect affects the wind turbines in the subsequent rows subsequent to the front one. So as you walk back through a wind farm, the wind turbines tend to be less efficient because there is more turbulence and less laminar wind. So downwind turbines can lose 20 to 30% of their power. Then we started to get offshore wind into the UK in the early noughties, and the government allowed people to bid for 30 machine offshore wind farms. And this map shows where the first ones were, or which sites were first selected. And some of them were two wind farm sites. For instance, this green dot here. Some of them were 1 turbine sites, the mauve dots, and other ones were 90 turbine sites. That meant that there were 3 bidders wanting to build a wind farms adjacent to each other. And there are about 18 sites in all. My company built the wind farm at Barrow offshore wind farm, which is, let me see now, number 2. We built Barrow offshore wind farm, and I'll come to that in a minute. All the wind farms were allowed a maximum of 30 turbines at that stage, and this was round 1. And it was just to get our offshore wind activity in UK started. And what do you need to build a wind farm? Well, you can use jack-up rigs from the oil and gas industry, but a company called Mayflower Engineering cottoned onto the fact that a custom designed wind turbine installation vessel might be useful. I was invited to go along and talk to the board of directors about producing a turbine installation vessel, and they wanted to know how to build an offshore wind farm. I explained to them how an offshore wind farm should be built, which was very good actually, as nobody had built an offshore wind farm in UK at that juncture. But anyway, I convinced them that building this this custom turbine installation vessel was a good idea, and they called it the Resolution, and it was the first vessel of its kind. It had a crane that was designed to lift 300 tons, and it was self-propelled jack up with azimuth thrusters and bow thrusters, and it was maneuvered using GPS, dead into position, and then it jacked itself up. I've got a movie of that, but I can't actually show it to you at this stage. But it was built by Mayflower Engineering, who made a lot of the bus and truck chassis in Europe and in North America. And they had some spare money, and they decided that they wanted to build one of these vessels. It cost $38 million. They actually didn't have any spare money. What they'd done was a lot of creative accounting, and they actually went into receivership soon after they built this vessel. But anyway, the vessel got built. Technically, it was a great success. Financially, it wasn't so good as a lot of things that are in the vanguard of their topic. It could carry a number of wind turbines, wind turbine blades, nacelles, and towers. First offshore wind farm was North Hoyle. It was built in 2003, 2004. The idea was that it was going to use the Mayflower Resolution for its build, but it wasn't ready in time. So they used some tug-towed jack-up rigs. We helped them get their round one license. We did the geotechnical survey, and we acted as a planning supervisor for that offshore wind farm. And you can see one of the foundations adjacent to the jack-up rig in that picture. And there is one of the foundations with its transition piece on it, and I'll come to that in a minute. And there we have the whole shooting match. And there is a complete turbine on the first offshore wind farm in UK waters. That's a 2 megawatt Vestas V80 turbine. Then we bid for a wind farm off Barrow, and by that time we were up to 3 megawatt wind turbines. And you can see the position of the wind farm on the left-hand side of the picture. 2 rows of 7 turbines and 2 rows of 8 turbines connected together, daisy chained together with subsea cables, and a long power cable leading to shore. The nearest point of land was fairly close to the wind farm, but the grid, the Cumbrian ring, wasn't strong enough to take the output from the wind farm. So we had to bury a subsea cable from the wind farm to Heysham Nuclear Power Station switchyard. That was 27 kilometers. And in order to do that, we had to improve the voltage from 33 kV to 132 kV to reduce the power losses. So we built the first offshore wind farm in UK waters with an offshore substation. And there is the layout of the Barrow offshore wind farm. And you can see as the cables get closer to the substation, they change color. That's because we needed heavier cables as the power along the daisy chaining increased. So there were larger conductors in the cables nearer to the substation. We designed the substation ourselves, with detailed design for the substation being input by RINA. This shows the foundation construction using monopiles, two concentric tubes, one at the bottom being the monopile and the one at the top being a transition piece, carrying all the J tubes, ladders and other impedimenta that you needed to get the power away from the turbine and also allow people to climb up it. The tubes are concentric and there's a gap between them. In case you don't get the monopile in quite vertically, you can improve the verticality by jiggling around with the transition piece, then pouring grout, pumping grout into the annulus between the monopile and the transition piece. And it's held in position with jacks while that is done. Take the verticality, correct the verticality. But I've not known a monopile be put in with an error of more than half a degree. Normally they get them in absolutely vertically, which is pretty good. There we used Holland and Wolf's yard for our laydown area for building Barrow offshore wind farm, as it was very convenient and they had a lot of space and they weren't doing anything else. So we wisely used their dockside as a laydown area, and the MPI resolution came backwards and forwards and picked an installation load up, took it out, installed it, and then came back. The distance wasn't particularly great between Belfast and Barrow. And there we are looking down from Holland and Wolf's gantry crane onto the resolution, and you can see monopiles ready to be loaded and taken offshore and hammered into the seabed. That gives you an idea of the monopile. 350 to 450 tons. I can't see what length I've written down to them, 50 to 60 meters, something like that. Outside diameter 4.775 meters. WT. I can't see what WT is. Can anyone read that for me? No.
It's 45 to 80 millimeters, Rupert.
Okay. Yeah, wall thickness 45 to 80 millimeters. Thank you very much. Some of them had to be drilled as well as driven, because sometimes the soils were a bit rocky, and it prevented the piles from being driven in without buckling. So sometimes some of the monopiles we had to drill the center out before we could continue with driving. And there we have the MPI resolution with a monopile. They had a gripper at the stern, which could, two grippers, which could maneuver it for verticality, north-south and east-west. And that's probably a 750-ton hydraulic hammer that's being used to bang it in. As soon as it came up against too much resistance, we put the drill in and drilled out the center, got rid of the boulders that were in it. You can also see on the MPI resolution the substation transition piece with the cable deck on top. So constructional engineering for us for KBR, monopiles, transition pieces, substation cable deck, and we had a very short time scale for doing the whole job. We got most of it finished on time. There were some delays due to problems operating the turbine installation vessel. And there is a foundation in place, monopile with the transition piece on top. 2 ladders. We put 2 ladders on because we wanted boats to be able to approach into the current at all stages of the tide, whether it's ebbing or flowing. And that's a picture of the substation at Barrow offshore wind farm. It won't win any prizes for architectural merit, but it was completed in a very, very, very short time. It's got we're humming and hawing about the number of transformers it should have, whether it should have 2 or 1. But the client in the end said, we just want 1. There's always a chance that a transformer might blow up. And we thought, well, if there are 2 transformers up there and one of them blows up, it might damage the other one. So we might just as well have one big one up there to start with. So that's a 132 kV transformer. In the containers on the left-hand side, we have the 33 kV switchgear. Large capacitor bank for power factor correction in case we needed it, an accommodation module, and the slightly darker grey container that you can see contains a small keep alive generator for the offshore substation. It won't keep alive all the wind turbines, but it keep alive the offshore substation should it lose power. So there are 4 array 33 kV tables coming into the substation and 132 kV output cable going to Heysham switchyard. On the right-hand side of the transformer is the 132 kV switchgear. And for firefighting, it had an Inogen water mist system, similar to the ones that you put into a ship. And for that, of course, we had to have a freshwater tank because they don't use seawater. Now we got up to Barrow wind turbines, 300 kilowatt turbines, capacity factor of 36% because the wind offshore is better than the winds onshore, more laminar flow. Power a year per turbine, you can see there. 1 home usage, again, 400 kilowatt hours a year. 3,365 turbine homes supplied by each turbine, and 70,000 homes supplied from the whole wind farm. But again, this was an early offshore wind farm, and things have progressed since it was built in 2006. Here is a typical subsea armoured cable. This is the 132 kV that we use 27 kilometres of to connect Barrow offshore wind farm to shore. Obviously 3 conductors, red, yellow and blue phase for the electricity, Weight 48 kilograms per meter, carrying 90 megawatts or 115 megavolt amps. 28,000 meters, so it weighed 1,344 tons. External diameter is about 170 millimeters. And there's a fiber optic running through it as well for the SCADA system. Steel stranded armor. And the conductor cross-sectional areas, each conductor was 300 square millimeters. And it had to be specially made by Nexans in Norway. It was made to order by Nexans in Norway. London Array was an offshore wind farm that we did a front-end engineering design study for. And this one is in the mouth of the Thames estuary. Until earlier last year, it was the largest offshore wind farm in the world. Power coming into a place called Graveney through 4 subsea cables. And each turbine here, they've grown slightly, 3,600 kilowatts, capacity factor 36, and we've got 496,000 homes being supplied by these 175 turbines in the London Array. It's still going strong. I've seen you can look up the Crown Estates website. I've seen during some of the windy weather, I've seen London Array producing 98.9% of its rated output. So if we look at where we are with wind turbines, first of all, windy standard with a 43-meter rotor diameter, 600 kilowatt turbines, 394 homes. And now we've got a wind turbine of 9,500 kilowatts, each one supplying 6,307 homes in Triton Knoll. And they just started putting the wind turbines up, I think, this month. The foundations are in place. Triton Knoll offshore wind farm is off Lincolnshire. And there's a story about the 800 kilowatt, 8,000 kilowatt, 9,500 kilowatt turbine that I relate with fairly closely. In 2009, I was asked to go along and talk to the House of Lords. They're having a meeting one evening, and or they were having a get-together with renewable energy people, not actually in the House of Lords, but in a hall near the House of Lords. And I was asked to, or I decided I would go along and talk to the House of Lords about, or the Lords about wind energy. Well, the Lords weren't too tuned up in having conversations about wind energy, but I saw 3 Japanese-looking guys, or 3 Japanese guys, standing in a corner, chatting to each other, not being entertained by the Lords. And I thought to myself, naval cocktail party routine, I better go and talk to these people and do a little bit of hosting myself. So I went up and started chatting to them, and I said, "Who are you?" And they said, "MHI." And I said, "Who?" They said, "Mitsubishi Heavy Industries." I said, "Oh." They said, "What are you doing here?" "Well, we're in charge in Europe of the sales and production or introduction of our wind turbines." And they made it, I think they made something like a 1.5 megawatt wind turbine at the time, so it wasn't all that big. Anyway, we exchanged cards, and a few weeks later, the top man, who was a tall Japanese guy, very tall Japanese guy, gave me a ring and said, "Can you come along and talk to us and tell us about how you build an offshore wind farm?" So I went along, and remember this was 2008, 2009, and told them all about it. Anyway, I didn't think too much about it. I gave them a presentation, and a few weeks later, they said, "Can we come and see you? We want you to do a job." And I said, "Yeah, sure, we'll come along and talk to us about what you want." So they said, really what they wanted was to know what the most economical size of turbine was per megawatt installed for a large offshore wind farm. What size turbine was the most economical one to build? And that included the offshore substation and all the installation works, etc., etc. And we came up with an answer of 7 megawatts. This was KBR. We said the best size you can make is 7 megawatts. So they went away and they thought about it, and we went and visited them in Hamburg a couple of times, and they thought that's a good idea. But then they teamed up with Vestas, and between them they produced a 7 megawatt turbine. And they found that that 7 megawatt turbine would produce 8 megawatts. And they ran it, and then they found it would produce 9.5 megawatts. And now they've found that if they tweak it a bit more, it'll produce 10 megawatts. It's got 164 meter rotor diameter. So each of the blades is about just under 80 meters long, allowing for the hub in the middle. So those are now being installed on Triton offshore wind farm. And I hope they're very, very happy with them, because there's a lot of development work gone on to these turbines. Triton offshore wind farm. Wind turbines now starting to be installed out there. We did an initial study for Triton offshore wind farm. We did a front-end engineering design study for Triton offshore wind farm. And this shows the difference between using lots of small turbines or a small number of large turbines. Now, when we did this study, there was no 8 megawatt turbine in production. It's only just been thought about. This was way back in 2008, 2009, again, about the same time as I went and talked to Mitsubishi Heavy Industries. With the large number of smaller turbines, you only get a capacity factor of 31%. And with the 158 megawatt turbines, you get a capacity factor of more like 38%, I think. I can't see what I've got written down there, because the people watching the presentation are in the way. So you're better off with a smaller number of large turbines than you are with a large number of small turbines. The capacity factor is better because the turbines are bigger, they reach higher up into the wind, where the wind speed, the wind gradient is improved, and they're in higher wind speeds. Also, you've got 150 turbines to visit instead of 333. And in fact, on that wind farm, they're going to be using now, they're building it, they're going to be using about 9.5 megawatt wind farms, wind turbines. Instead of jacket substructures, you can have, instead of monopile substructures, you can have jackets. That shows the Beatrice demonstrator project, which we did the front-end engineering design for and the consultancy work. And you can see that it's put on a jacket, which are much more expensive to produce than monopiles, but they suit deeper installations. Sometimes they're found to be beneficial, but monopiles have got bigger and bigger as we've gone through development stages. Huge monopiles being made in Roscoff in Germany now. Anyway, Beatrice demonstrator, 5 megawatt turbine, That was built several years ago on a jacket. There were two of them. They've now built a whole wind farm up there. It's in 45 meters of water. Talisman Energy wanted to make a demonstration wind farm in much deeper water. Up till then, water depths that wind farms have been built in have been up to about 18 meters. And there are jackets being made by Burnt Island Fabrications in Fife. The chap that's built, owned Burnt Island Fabrications or managed it was a man called John Robertson, and he was absolutely determined to bring work for wind turbines and offshore wind farms into the United Kingdom. Unfortunately, he worked far too hard at it. He never took time off. I knew him quite well, and eventually he put so much effort into him that he gave himself a heart attack and died. He was never out on the golf course at weekends. He liked golf, but he was so busy working that unfortunately that's what happened to him. And they don't make jackets anymore, but he did keep a lot of people in the depressed area of Fife employed. Concrete gravity bases. Well, civil engineers love concrete and they like concrete gravity bases. They're not very effective. They used gravity bases at Thornton Bank in Belgium, but this was basically to give the Belgian people some part to play in the manufacture of this wind farm. So they produced some gravity bases for it. Although a lot of the turbines on Thornton Bank are on monopiles, but they are very expensive to build. They take, when you put the rebar in, you find that they take almost as much tonnage of steel as you would put into a pure steel base, although it's only rebar steel rather than a more fancy offshore steel. The average concrete used in each gravity base was over 1,000 cubic meters, and it took 135 days to construct each gravity base with the number of pours, concrete pours that needed to be done. So although it was a good experiment and it gave some Belgians some fabrication input to the wind farm, it really wasn't very efficient. 250 tons of steel, 215 tons of steel reinforcement. Probably if they'd put monopiles in, it would have been 500 tons, but they would have been made a lot quicker. And there are the concrete gravity bases for your interest. Thornton Bank. I don't know of any other place where concrete gravity bases have been used. And there is a very large monopile, much larger than the ones that we were using in Barrow. And this is made at Roscoff and is going to be used at Borkum Offshore Wind Farm in the German Bight. 6 megawatt turbines. That one is 1,302 tons, 7.8 meters diameter, and it's in a 33 meter water depth. They do have very bad ground in Borkum Offshore Wind Farm in Germany, very bad ground indeed. So they need quite a large penetration into the soil because it's rather rubbishy and loose on top. Well, I've told you about the Vestas 8 megawatt turbine with 164 meter rotor diameter, which is now a 9.5 megawatt turbine being put on Triton Knoll. and there's going to be a 10 megawatt turbine eventually, and you can get a version with 174 meter rotor diameter. Anyway, we came up with 7 megawatts, went to 8 megawatts, 9.5, 10, and there'll eventually be 174 meter rotor diameter. Just shows how things have progressed in the last 24 years since I started off in the wind energy industry. And the largest wind turbine is GE. It's going to be put on the Dogger Bank in 2022. And the Dogger Bank will be 3,500 megawatts altogether from a 12 megawatt turbine. And I think it's got a 212 meter blade diameter, a rotor diameter, I'm sorry. So each blade is about 100 meters long. And there will be DC power transmission from that, with an offshore converter station and an onshore converter station. Quite expensive, but minimized power losses. So that's the largest wind turbine about to be put on the Dogger Bank in 2022, 2023. 220 meters rotor diameter, 107 meter long blades. Now that turbine installation vessel, the Revolution, and its sister ships that have been built, and all the wind turbine installation vessels that we have until recently won't touch these new turbines. They've become pretty redundant apart from servicing the old, smaller offshore wind farms. And we now need something much bigger in the way of turbine installation vessels. And here is one, Jan de Nul, and it's got a crane lift capacity of about 3,000 tons. It's another jack-up one. Low emission engines, dynamically positioned, but we've gone up to needing a 3,000 ton lift crane, the Voltaire. And that one might not be big enough. So we've got a turbine installation vessel now with a 5,000 ton lift crane. Both these vessels are made in China, built in China. This one is not a jack-up, it's anchored in position. And I think it's got tanks for stability, ballast tanks that you can move the ballast around in fairly easily. But being naval architects full-time, you know much more about that than I do. So 5,000 ton lift capacity, which puts the Resolution's 300 tons crane a bit in the background, and it was converted to a 400 ton crane. There's some floating wind turbines. Three different sorts, a pendulum, tripod, and anchored. Tension leg one. We're yet to see how those work out, but they are expensive compared with ones that you can fix to the seabed. That's a movie. Anyway, I've come to the end of my presentation now, and this is just a reminder of where I came from. That picture I took when I was a midshipman in 1964 at the age of 19. And that's, for those that remember them, that is a Leander class frigate, all of which have been scrapped by now. And we're about to refuel it from HMS Tiger, which was a cruiser.
Rupert, that's my old ship there, HMS Penelope.
Which one?
F127.
Was it?
Yeah, first ship I
Relative.
joined in 1974.
What were you?
I was well, I ended up as a navigator's yeoman on
Oh,
Leander's.
right, okay. Well, the ship, as you see it there, was brand new, and it's
Yeah.
just off for a trip around South America.
See, she's still in the. She was in the second frigate squadron when I joined her.
Well, it's got a 2 on the funnel now.
Yeah.
Yeah, yeah. She came alongside. She'd been delayed because she had a machinery problem, and she was due to not need to refuel from us, but she steamed and caught us up at full chat, and needed quite a lot of fuel. So Tiger, carrying a lot of fuel, refueled her until we caught up with an RFA.
When I joined her, they'd taken the 4.5 off, and we were testing the new Seawolf missile.
They didn't look as nice then.
No.
They didn't look as nice. Anyway, that's the end. Thank you for listening. I hope you've enjoyed the talk and it's been informative. And now I can take some questions from you if you've got any. But they gave me a nice 4-wheel drive to build Windy Standard wind farm with. So that's me with it in the November snow in 1996, after we got all the machines up and running. Can I stop the share? Can I stop the share now?
Yes, thank you very
Thanks.
much, Rupert. That was really very interesting. Does anyone have any questions for Rupert?
There's a question in the chat that it says, may I ask you, do you think they will have, no, what? It says, thank you for the talk, Rupert. It has been very insightful. Autonomous systems have come a long way in the last 10 years. May I ask you, do you think they will have a notable impact within the wind power industry in the next 10? And if so, 10 years? And if so, what parts of the industry would see the most impact? Thanks, Joe.
Well, I think we're going to have a lot more offshore wind farms, and the bigger the wind turbines are, the better the capacity factor. And they're talking about having, by 2030, they're talking about having an 18 megawatt wind turbine with a capacity factor of between 50 and 60%, because it'll be so much taller. And as they get bigger, and you have to put less of them offshore to get the same power output, the unit cost per megawatt installed starts to come down, and it's come down remarkably in the last 20 years, the installed cost of a wind turbine. But to make them more expensive, they're going to need, as the further they get offshore, they're going to need conversion to DC and a heavy DC cable bringing the power to shore, then conversion back to AC again with rectifier static inverter stations. But are you well versed with electricity? Because I'm sometimes conscious that when I talk to some people, they don't perhaps have a great understanding of high-powered electrics. I don't, but I learned it. I learned enough to come up with the good buzz phrases when I'm giving these talks. But power electronics are getting cheaper all the time as well.
Rupert,
I think we're going to see a lot more wind farms. I think the government is talking about developing 4 times the capacity of offshore wind that we've got at the moment. And we need gas turbine, combined cycle gas turbine power stations to back up when there's no wind. Because what we're going to need probably is a lot more nuclear power to satisfy our insatiable need for power, for green power. And the government is heavily in debt at the moment, but what we really need, we think, we engineers, I'm in a group of engineers who are going deeply into this topic. We think we're going to need a lot more nuclear power stations like the French have got, and we need to start in earnest on a nuclear power development scheme right now.
Rupert, thank you. It's David Monks here. Thank you very much for an interesting talk. I agree with what you say about nuclear power stations that we're going to need. But coming back to wind farms, in the early days, there was a big problem with the gearboxes. And what I was told is that the very high pressures on the gear teeth was such a problem that they were having difficulty inventing and developing the oil that was needed to take those pressures, and caused quite a few explosions and fires. Can you say anything about that?
The main problem with the gearbox was with the Vestas V90 3-megawatt wind turbine. I've got pictures of it. It was a very, very advanced gearbox, and they kept on cracking up. At some wind farms, at Barrow, I think they had 2 gearbox changeouts. But it wasn't the high pressure on the gear teeth that was the problem. It was the design of the bearings that couldn't take the shuddering from the wake effects of the wind turbines in front of it. And what they had to do was redesign the bearings, because the gearboxes haven't got any bigger. They just changed, well, they might have changed shape slightly, but it wasn't it didn't seem to be the gear teeth that were the problem. The gear teeth weren't failing. It was the bearings in them that were failing. And we had to do that in the Navy at one stage with our new gearboxes and the counter-class guided missile destroyers. Instead of using the old OM-100 straight mineral oil, they used OEP-69, extreme pressure oil with a sulfur compound in it, like you put in the back axle of an old car.
Yeah.
But I don't remember being told about any problems with the gear teeth not being able to take the load. It was to do with the sort of bearings they were putting in, and they had to redevelop the bearings.
Thank you.
Robert, Michael Howard here. You mentioned the factor for the fact that the wind doesn't always blow, and you mentioned efficiencies in terms of the output. But what about downtime for maintenance? How does that affect efficiency overall?
Well, they do break down, but what normally happens is you shut a wind turbine down for 2 days a year and do campaign maintenance on the whole fleet of wind turbines in a wind farm. And that's normally in the summer when winds are lower anyway. And what they do is they go out there and they change the oil and do all the other good things that you need to do to a wind turbine, and then come away again. And each turbine takes, well, the story was that each turbine took about 3 or 4 men 2 days to maintain in good weather.
Thank you.
You know, if a turbine packs up and the weather is too rough, you don't send people out there to fix it. You leave it till the weather calms down. Most substations have a helicopter landing deck on them. So if a substation goes down, which in bad weather, which means you don't get any power from the wind farm at all, they'll send somebody out to fix what happened on the substation. But most of these things can be monitored from onshore from the SCADA system, and a lot of them can be corrected at the other end on a chap sitting at his desk with a computer.
Sure.
Yeah.
Rupert, it's Colin. I was interested in your comments in terms of how the vessels serving the wind farm industry have evolved over the years. I sail as master of various crew transfer vessels working the wind farm industry, mostly in Germany, Holland and Denmark. I noticed you mentioned the Balkan Rufgrund. I worked on that one for about 18 months, 2 years. And as you know, it was about 45 miles steaming from Nordyke to get out to the actual wind farm. We used to have to cross the tertialing traffic separation scheme, which is quite interesting at times, trying to dodge all the big container vessels going into Hamburg. But I noticed that now, you know, we would carry sort of 12 passengers and deck cargo in those days. Now the vessels have evolved out to like these walk to work vessels, and I do remember on Borkum they used to also use helicopters, but I think that's too expensive these days. So it's interesting to see how vessels have evolved over the years.
Yeah, well, there was one stage, there was a lot of effort put into the design of vessels for servicing offshore wind farms, and nobody really came to have a good solution as to how you step off a turbine support vessel onto a turbine in rough weather. So I think they tend to concentrate on health and safety now, and they don't go and visit turbines in rough weather.
I noticed that when you showed the picture, the Barrow one, it would be a dream for most masters to have a ladder facing to the side. I've never worked on a wind farm that's given us that choice. I think there was a couple of towers in Germany where there was two ladders. Generally, it was the one ladder, and you had to be able to maneuver in all weathers to get them onto the ladder.
Yeah, well, there was a bit of naval input from me for Barrow Offshore Wind Farm, and I suggested that we put a ladder on both sides facing the tide. I don't actually think that they worked out too well in the end. But what you do is you keep slight forward motion on the vessel, and the pointed bow goes into two upright fingers to hold it in position. Then you jump across. And then on some of the wind turbines, depending on the state of the tide, you've got a hell of a hike up a ladder to get into to get onto the platform.
Thanks.
Yeah, but all the wind turbines now have got lifts in them. Any more questions?
Yes, thank you very much for the presentation, Rupert. Having looked at the wind farm for many a lunch hour from a certain shipyard in Barrow, it all looks very impressive. I was particularly interested in what would be the limiting factor when you reference a 25-year design for these structures. And in particular, I would be interested to just know what fatigue problems have occurred on the earlier structures, having been involved a little bit when they were being produced.
Well, the foundations are designed for a 20-year life or 25-year fatigue life. But what the history is and what records have been taken since wind farms have been built, I don't know. But I think what they do is they use a sensor to measure the movement of the structure in the sea and see how much more movement they get year on year. But I've not heard of any offshore wind turbine foundations failing, although I do understand that Beatrice, the demonstrator wind farm, has had problems with cracks appearing in its jacket foundations. We originally designed a tripod foundation for it when we did the feed study or the consultancy study for the wind farm. But by the time we didn't win the job of actually building the demonstrator wind farm, but Nordic Tower designed the jacket structures that it now sits on. And I did hear a rumor that there had been some cracks appearing. It's a very lightweight structure.
Thank you.
But 25 years is the design life of wind turbines. We've said to wind turbine owners, power companies, would you like us to design the foundations for 50 years so that you can re-turbine it after 20? And all the accountants said, no, we just want it designed for 20 years. But I'm sure that with the factor of safety that have been built into most of them, they will last quite a lot longer than that. But I haven't got any up-to-date information on fatigue failures.
Okay, thank you.
Do you think we're approaching a maximum rotor diameter for wind turbines at the moment, or do you think we're a few years off that yet?
Sorry?
With wind turbines at the moment, do you think we're approaching the sort of maximum rotor diameter in terms of materials limits, or do you think we're a few years off that yet?
No, they say we're going to get an 18 megawatt turbine, 18 megawatt turbine by 2030. So goodness knows what that'll be. That'll be a larger rotor diameter than 220 meters. So I think we're going to see bigger turbines. And they will have a capacity factor, so the government thinks, of above 50%.
Just through sheer height.
Sorry?
Just through sheer height, I said.
Yes.
Yeah. It's not a very good microphone, sorry.
Yeah, I'm going a bit deaf.
Rupert, Michael Howard here. Are there any plans in place for the decommissioning of these wind turbines?
Yes, before you build an offshore wind farm, the requirement is that you have a method for decommissioning it.
Right.
And you're also prepared to put up the money to decommission it when the time comes. Most of them are very easy to decommission because all you do is reverse install them, take the blades off, take the nacelle off, take the tower bits down, and then you're left with a foundation which you can grip blast off below the mud line inside and lift most of the foundation away, just leaving a small portion of steel sitting in the seabed.
Right.
And whether you pull the copper cables up or not, I suppose depends on the economics of copper at the time. Whether you pull the array cables and the transmission to shore cable up or not, or whether you leave it there.
Yeah.
Depends how desperately anyone needs the copper.
What about the disposal of the GRP components?
That's a problem. It's just raised its ugly head. Someone in the States has started decommissioning wind farms, and they found that they've got thousands of tons of GRP blades that they haven't really got a use for.
Yeah.
But I'm sure someone will come up with a useful solution for using it. Don't know if you could use them for aggregating concrete, if you broke them into little bits, for instance.
Yeah.
Yeah. But
it's a subject that I've been looking at in terms of GRP boats. I've been doing some research over the COVID lockdown, and the same thing applies to those. There's no real there's a lot of decommissioning cost and no resale value.
Yeah. So what are you going to do with the GRP for boats?
Well, same as the blades, smash it up and hopefully reuse it in some low cost, low density material, such as using it in reinforcing in concrete, or actually using it together with thermoplastics to make materials for park benches and such like.
Yes. Yeah. You've got to grind it quite small for that, though.
You have, yeah.
You can have bigger lumps for your aggregate.
Yeah.
Yeah. Yeah. No, it's a recognized problem. Yeah.
Rupert, I have a question in regards to these big future 18 megawatts turbines. Will be these mainly used for the floating offshore wind?
Well, I don't think we've got far enough into the development of offshore wind turbines at the moment. When push comes to shove and we haven't got any more room close to shore to put turbines on foundations, then I expect people will start thinking a bit more about floating wind turbines. But they are about 3 times as expensive as ones that are on gravity foundations at the moment. I'm sure the price will come down as we develop the techniques for them. But the main problem is a long distance from shore, cables going down from them to the seabed, and getting the power cable down to the seabed and connecting it up to all the, in an array, to all the nearby wind turbines. That's why we look for shallow water at the moment. The Triton Knoll's in fairly shallow water. The Dogger Bank is reasonably shallow, and we're going to have big wind farms out there. But they are working on floating wind turbines at the moment. We just have to wait and see what the developments are forthcoming. And cost.
Yes, I've heard will be the biggest one will be in Kirkcaldy in Scotland, like the floating one. But
in Kirkcaldy.
Kirkcaldy, yeah.
Kirkcaldy.
Yeah. Kirkcaldy, I believe.
Okay.
But,
well, if they got deep enough water there, fine.
But the main drivers for these high costs are not actually the structures of the turbines. It's actually the transmission.
Yeah, it's the turbines, I think, are the same. It's the high cost is to do with the construction and putting the anchors on the seabed and the cables down and that sort of thing, and the anchor cables. You may need five strands to hold them in position.
Right. Okay.
And doing things in deep water, of course, is much more expensive than doing things in shallow water normally, in any sort of construction work.
Yeah.
Will
be the floater structures strong enough to take the forces of such big turbines, or will be a limitation as well?
Sorry, I didn't quite get that.
For these big turbines, will be the floaters, like the supporting structure of the turbine.
Yeah.
It will have any limitations? How much load a design can take? A cost-effective design for supporting such big turbine in such a big deep water.
Yeah, I don't know. They're experimenting with them at the moment, Gabriella, and we'll just have to wait and see what happens.
Are they willing to share any data of their progress, or it's quite a closed market?
I don't know the answer to that one.
Okay.
It is prototype test wind turbines, floating wind turbines that are being installed at the moment. And I think there's some funding from somebody for it. I don't think they're completely commercial. So data may well be available, but I don't know the answer.
Oh, thank you. Thank you so much, Rupert. And thank you so much for your insights. Very much appreciated.